I'm Rosalie Lopez, the president of the Planetary Sciences section. In this session now, we highlight our Planetary Science Section Award winners for 2020. The Ronald Greeley Early Career Award for 2020 is given to Dr. Juan Manuel Lara, Assistant Professor of Earth and Planetary Science at Yale University, who is being honored for his work on planetary climate, including general circulation models, hydrologic cycles, and paleoclimate. This award is named after Professor Ron Greeley from ASU. Ron was a mentor to me and to many students and early career scientists. We thank Ron's wife, Cindy Greeley, for her support of this award. In fact, she has been coming to AGU every year to congratulate the award winner in person, and we hope she can meet Juan next year. I'm sure Ron would have been delighted with our choice this year. Many congratulations, Juan. The lectures now are the Shoemaker and Whipple lectures, which are a highlight for our planetary scientists at AGU. Our 2020 Shoemaker lecturer is Dr. Jack Hunter Waite from Southwest Research Institute. Hunter is a planetary scientist specializing in the application of mass spectrometry to the study of solar system evolution and astrobiology. He's involved in research projects in ion and neutral gas spectrometry, gas chromatography, geochemistry, and atmospheric modeling. He has a degree in physics from the University of Alabama and a master's and PhD in atmospheric sciences from the University of Michigan. He has participated in several space missions, including Cassini, in which he was the PI for the ion neutral mass spectrometer and the plasma spectrometer. His lecture today is on CASSINI'S Chronicle of Carbon in the Solar System. Welcome, Hunter, and congratulations on being selected to give today's lecture, which is named after planetary scientist Eugene Shoemaker.
Hi, and welcome to the virtual Eugene Shoemaker Award Lecture session. Today I would like to discuss with you the fate of carbon within the SATURN system. I will provide a brief introduction, followed by a discussion of the carbon compounds from the rings, Titan, and Enceladus, three of the most important sets of information on carbon compounds that we acquired during the mission. It's very important to acknowledge the many people that have contributed to this investigation. Graduate students are listed in the top left-hand corner, as well as key scientists that work with me on Cassini on the left-hand side. In addition, there's a whole host of people that were involved in the INMS team. Of note is Rebecca Perryman and Greg Fletcher, who served as the operation team leaders over the course of the mission. On the right-hand side are people from the Cassini Huygens Project Science Group that I worked very closely with. I'd like to point out a special tribute to Hasso Niemann, formerly of Goddard Space Flight Center, who, without his work to build the ion neutral mass spectrometer, none of this work would have been possible. One of the main attributes of the Cassini-Huygens mission was the international collaboration that was taking place. The flags represent 19 countries that participated. In addition to NASA, ESA, and the Italian Space Agency made major contributions to the program. Cassini has demonstrated itself to be a major scientific accomplishment of exploration in the Saturn system. And I'd like to just briefly touch on what led to that success. First of all, as I've already mentioned, the true nature of international collaboration is extremely important in its success. Another thing is a highly capable group of scientists that were operating the various instruments, that learned how to work together carefully and learned to appreciate exactly what each instrument contributed. Because in the end, the sum was greater than the than the parts. Each instrument made a contribution, but the contribution from all of them combined made the science that made a lasting impression on us. Finally, there's the realization that nothing ever goes according exactly to plan, and our ability to adapt to situations, to get new science, things like the serendipitous discovery of the plumes of Enceladus were extremely important in shaping Cassini-Huygens. And finally, in tribute to Eugene Shoemaker, the importance to me was an atmospheric scientist that learned to appreciate geology, albeit with the help of his colleague Larry Soderblom. In this video, we see the launch of the Cassini-Huygens spacecraft in 1997 from the Cape. It was a very beautiful launch with an entry into the clouds and an exit through the clouds that made us all pause in awe. The mission, as I say, was launched in 1997. In 2004, it arrived within the Saturn system. And the end of the mission was in 2017. So it lasted for almost a half a Saturn year, over a many-year period, but we got to see the seasons change within the Saturn system. That was a very important part of piecing together the overall exploration. In this slide, we show the Cassini ion neutral mass spectrometer, which is one of the central instruments that I'll talk about in this talk. It utilized 3 different operational modes. One was the closed source neutral mode, where gas is trapped in this, thermalized in this antechamber. Issue there is that the molecules can impact the walls, leading to fragmentation at high velocities. And it also, there are reactive species that chemistry might take place upon the wall interaction. The second mode is the open source neutral beaming mode, where particles came into the open source, which is located, as you can see in this slide, the entrance below the closed source. In that case, the material was ionized before it ever touched the walls and never touched the walls, so reactive species could also be measured. And finally, the open source ion mode, ions come into the same open source and there's no further ionization because they're already ionized in the ambient environment, and they are turned and measured in the mass spectrometer without ever touching the walls again. There are a few caveats to this that we need to discuss. As I've already mentioned, molecules at flyby speeds can fragment on impact with the antechamber. This happens in the closed source, but the closed source is about 1,000 times more sensitive than the open source, so it was used for most of the mission. So that is a limitation that we have to keep in mind. And the closed source was made of titanium, so if there's ice grains that hit the surface and titanium vapors released, there can be reactions that we have to take into consideration. In the veneer of the various objects that we're looking at, in the case of Saturn, it's the rings, but it's in between the rings and the planet. And that indicates pristine material that is falling from the rings into the atmosphere. A second region where we made key measurements was in the upper atmosphere of Titan, where most of the interesting organic chemistry was taking place. And the third place was in the plumes of Enceladus, which gave us a unique opportunity to look at material that came out of the internal ocean and was measured as we flew through it. So in this sense, we have some unique opportunities to measure characteristics of the system that are quite different from what one would anticipate from a normal atmospheric situation. Let us start at the end with the grand finale and talk about mass inflow from the rings. In this simulation, you can see the trajectory of Cassini as it flew from high latitudes through the ring plane and out. The idea of examining this material was came about in the late 70s and early 80s when measurements were first made of the ionosphere. In this particular case, those ionospheric measurements indicated differences in the chemistry that were not expected and implicated the ring system as a source of water that would change the ion chemistry in the upper atmosphere. A couple of papers noted on the screen in that early work showing the data, first on the left of the ionospheric measurements, and on the right, the paper that first talked about the infall of water and how that might affect the system. So this is kind of a backdrop for why we were wanting to look at this region in between the rings and the atmosphere. This shows a little bit about the geometry. On the left, you see a view from the pole looking down as we flew through the edge of the rings, and you see the ring in the upper portion of the figure, the rings, and in the lower portion, the atmospheric boundary. In between, we made measurements at several different altitudes, which is indicated in the figure on the right that shows a cut from looking in the equatorial plane, a cut in latitude, and shows that measurements were made closer to the rings at some time and closer to the planet sometimes to help us to put together the picture of infalling material coming from the rings and falling into the atmosphere. We had certainly expectations from some of our remote sensing observations about what the atmosphere should look like. This slide shows three different solid lines that indicate hydrogen, helium, and methane, which were thought to be major components, and as they were originally modeled. As you can see, the data is shown with a series of dots that look like, that blend together in this particular slide. And you can see that the hydrogen and the helium, so the orange is the hydrogen and the red is the helium, were pretty much according to expectation. What was unexpected is the blue, which was the methane. And because the methane was, the mixing of the lower atmosphere was not supposed to persist to very high altitudes, the methane was supposed to fall off as a result of the lack of mixing and the difference of diffusively separating because it was heavier than the rest of the atmosphere. But what you can actually see is that there was methane measured up high. This is our first indication there was much more than water that was just falling out of the rings. Methane had to be one of those components. This shows a spectra that indicates the complexity taken from three different orbits. Notice the amount of material that we indicate ranges from about 5 to 40,000 kilograms per second, a huge amount of material. The hydrogen and helium, which are on the left side in brown and yellow, were pretty much as anticipated and are the atmospheric components. Much of the rest of the material that we see is infalling material from the rings, and that involved CH4, CO2, water, ammonia, and also, and you can see in the pink color, organics, a whole host of organics. Since we were flying very fast through the atmosphere, we quickly realized these were fragments of much larger organic grains that were falling into the system. Fortunately, we had other instruments that were making measurements to help us verify this so that we could have an independent way to determine that there was indeed grain-like organic material falling into the system. This shows the data from the MIMI instrument, which was measuring the large end of this grain distribution that was about 50,000 AMU. That was just the tip of the iceberg of the material that was later fragmenting and being measured by the INMS instrument. This slide shows the distribution of material. It's a volume mixing ratio for different flybys. For CH4, NH3, H2O, mass 28, which could be N2 or CO, CO2, and then the organics, which are shown as 56U. These indicate the different flybys, and if these are all grouped together, then this suggests there's an extended region over which this material is infalling, and it was gaseous when it left the rings itself. If they're distributed, as the case of NH3, H2O, and the organics, and they're spread out from one flyby to the next, this indicates that those materials came in as grains in a very discrete fashion. So there was a mixture of grains of material that involved water, ammonia, and the organic materials, and there was also the gases that were distributed as part of the atmosphere of the rings themselves, which included CH4, CO, and CO in this particular case. And perhaps CO2. CO2 is kind of on the borderline. It has to do with the temperature at which this material sublimates. So let's talk a little bit about the atmospheric effects of the infalling ring material, because this is what is of most interest to us with regard to the Saturn system. On this slide, we show the ionospheric measurements on the left-hand side. We show the electron content as well as the light ion species. And we show that the ions don't equal the electrons, which means they're missing ions that we're not seeing with our instrument that are at higher masses. And they come from complex reactions with this infalling group of volatiles that we've mentioned, like water, ammonia, CH4, and so forth. So on the right-hand side of the figure are shown several different models by Luke Moore that indicate the complexity of the ionospheric composition at these equatorial latitudes that is created as a result of this infalling material. In this particular case, the different panels indicate different assumptions about whether N2 or CO or C2H4 at mass 28 is the major infalling material. This slide indicates, it shows that the time over which at a given altitude the infalling material would equal the material that is present in the atmosphere. So it gives an indication of how the atmosphere might evolve over time from this infalling material if the inflow remained constant. And you can see that at altitudes where measurements had been made before, which is indicated by that line, that it takes tens to hundreds of millions of years, depending on the actual flux, to change the atmospheric content. But it's important to keep this in mind because at those altitudes, the amount of carbon in the system was about twice that at Jupiter. And so that may not represent the total body, it may represent a veneer, but it certainly is an important consideration about the evolution of atmospheres within planetary systems. This is a mechanism that has been suggested by Estrada and others that suggest how one might use the rings to provide a source of this infalling material over a long period of time. This shows the impact of micrometeorites on the system that once they impact their ballistic transport will transfer angular momentum outwards and material inwards. So their calculations indicate that the amount of material that was infalling, 10,000 kilograms of material per second, it could be supported for a very long period of time by just using the rings as kind of a way of trapping incoming meteorite material. So this suggests a mechanism whereby the rings can participate in the evolution of the atmosphere over a long period of time. Another potential indication of this comes from the dynamics. You can see over on the right side, the offset or the infalling ring material is kind of indicated with the light brown or yellow. It's a very narrow region of about 2 or 3 degrees in latitude. And over on the left side of the figure, you can see the wind system that has been measured by the CASSINI'S spacecraft. And you can, if things that move up off the baseline of 0 indicate that the winds are falling off. They're measured at different altitudes in this figure in difference. So they're falling off with altitude. The velocities are if you move up, and if you move down, and they are increasing in velocity as you move up in altitude. And you can see that this small 2 or 3 degree region in the center is moving faster at higher altitudes than at lower altitudes and would indicate a momentum forcing from above. Again, something that could happen from a continued infall of ring material over tens of millions of years. Finally, let me just try to put this into context from the chemistry point of view. I'm going to use throughout this quantity Z sub C, which is the oxidation state of these carbon compounds. And I indicate on the right-hand side of the figure the cometary input, and on the left-hand side of the figure carbonaceous chondritic material, both of which have been implicated as materials that form the Saturn system. And you can see that the Z sub C number for the Comet 67P is about the same as the ring material that was measured infalling, although there's a fairly large error bar, as you can see from the infalling ring material. These numbers are derived from the formula that is shown there, where we take the elemental composition of what we measured and determine the oxidation state. Comets can range over a fairly large value between 0.61 and 1.35. So 67P happened to be a volatile poor comet, and this is the same class as we've measured in this particular infalling of ring material. Again, the carbonaceous chondrites fall in about the same range. So it looks like that we probably are sampling potentially pristine material as we're looking at this infalling material. Now let us make a transition to the ocean worlds that are seen in the Saturn system. And we cannot mention ocean worlds without mentioning the term habitability. There's three criteria here that are listed. The liquid waters, one of them, abundance of complex organic molecules, and energy sources to sustain metabolism. So as I talk about the carbon chemistry of Titan and Enceladus, I'll try to point out these attributes. Titan is the second largest moon in the solar system. It's got a very thick atmosphere. It's got a surface pressure that is about 50% higher than the surface of the Earth. It's made largely of N2. It's very cold. The surface is 97 degrees Kelvin, which is quite cold. It happens to be at the triple point of methane, which is the second most important constituent. Triple point means that it can exist as a vapor, a gas, or a liquid. And we see evidence of all three forms in the system. We see it in vapor, we see methane rain taking place. So there's a methanological cycle that is very akin to the hydrological cycle that we see on Earth. And we see things on the surface that make that abundantly clear. So this is a slide that indicates that. In the lower part of the panel that you can see the hydrological cycle or methanological cycle that I'm talking about, where methane evaporates, forms clouds, and rains back out. There's lakes all over the northern polar cap and some in the south. So there's huge seas of methane on the surface. But it also indicates a longer climatological cycle that takes place where methane comes up with nitrogen, is ionized in the upper atmosphere where a neutral mass spectrometer was taking the measurements, and does a complex chemistry that leads to the formation of organic aerosols that ultimately end up on the surface. And one of the examples of those surface materials are large regions in the equatorial region of organic dunes that are made up of this processed material once it reaches the surface. So let's go through a little bit of this overall process, particularly the long-term process that takes millions of years to take place. This slide shows information from the caps in the ion neutral mass spectrometer. In the center is shown at the top, the neutral composition that we measured from 1 to 100 AMU, and in the lower panel, the ion composition. And you can see we've kind of color-coded it at the peaks, sets of peaks, to indicate that there's a strong interplay between those two. So there's a growth of carbon-bearing compounds that takes place as a result of ion-neutral chemistry. And we can see on the left, in the upper panel, positive ions that extend to much higher masses that are part of this interplay of material as well. And in the lower panel, at a lower resolution, an indication that there are also large negative ions that are formed, very high masses, up to tens of thousands of AMU, that constitute the monomers that are in the lower atmosphere or at lower altitudes, form the aerosols that enshroud the planet. And the figure on the right gives a schematic of how this takes place. This slide shows a Titan mass spectrum. In the lower left panel is the mass spectrum as we measured it with the ion neutral mass spectrometer. And surrounded in various frames are the major compounds and what their mixing ratio values are. And on the right-hand side, you see at the top the hydrocarbon compounds that we measured. And in the lower right-hand side, you see the nitrile compounds that we measured. Nitriles became an important part because of the ionization of N2, or the molecular nitrogen in the upper atmosphere, that became part of the chemistry that with methane to form more complex organics. And the dots in the figure just show that how we have deconvolved what these constituents are by analysis procedures that we developed over the years for the ion neutral mass spectrometer. This slide shows lower altitudes. The first slide was at about 1,000 kilometers above the surface. This slide shows 100 to 200 kilometer altitude spectra from the infrared, in this case, remote sensing of infrared species. And you can see many of the same hydrocarbons and nitriles are seen in the infrared at lower altitudes. This measurement was made by the CHRONICLE instrument on board the Cassini spacecraft. This slide allows a comparison between the two. So in the table, there's two columns that indicate the compounds are indicated the INMS, the CHRONICLE volume mixing ratio measurements, and the ratio between INMS and CHRONICLE, and some indications. NP indicates nonpolar, because there's going nonpolar, and polar molecules will participate in different ways in condensation processes, and R indicates that chemistry might also take place because these are fairly highly reactive compounds. But the clear message from this is that in all cases, to varying degrees, we see that there is more of these compounds from a volume mixing ratio point of view in the upper atmosphere than there is in the lower atmosphere. So the source of most of this complexity of organic material that's generated happens at the highest altitude through these ion neutral reactions. This slide indicates the parachuting in of the probe, and the spectra that is shown is obtained by the probe at about 120 to 130 kilometers altitude. You note that there's somewhat of an absence of these compounds that we've been discussing. At this cold temperature in the atmosphere, most of these compounds have condensed onto the aerosols that are formed. These compounds are being carried to the surface on the aerosols. In the next slide, we are actually taking a spectra from the surface itself, and this shows actual footage of these are ice rocks now on the surface of the planet. But now you can see these hydrocarbon compounds are emerging in the mass spectrum. And this happened because we landed on a dry lake bed, an old methane lake bed, and the material that was trapped on some of this material, once the spacecraft hit it, it warmed up the 97 degree Kelvin surface, and this material started to sublime. So we started seeing more and more complexity, the material kind of boiling out of the surface material. In the next slide, we can see a couple of the things that I've already mentioned, but I'll just reiterate. We see the atmospheric hazes caused by that form thick aerosol layers at high altitudes in the stratosphere and mesosphere. And on the right-hand side, again, we see the location of these dark regions or equatorial dunes that are made of organic material, which we don't completely understand the chemical processes that form these at this point in time. But we're quite sure that most of the material that forms them originated high in the upper atmosphere from these, from the interaction of the sun with N2 and methane. This shows an indication of the hydrological cycle that I've already mentioned. You can see a picture of the clouds on the left-hand side, and you can see a radar map of the methane lakes, or some of the methane lakes that are seen in the northern hemisphere, all a part of the hydrological or methanological cycle on Titan. In this slide, we also indicate that measurements from gravity and other measurements on the probe indicated the presence of water in the interior too. But it's several hundred kilometers below the surface, and it's not necessarily in contact with the rocks to provide interesting geochemistry we'll talk about when we get to Enceladus. But it does show that there is water present, and the open question is, can it move down or up through the ice to interact with all these surface organics? Because we know from previous laboratory investigations that once you bring liquid water into contact with these organic materials, they form amino acids, which are important building blocks of life. And finally, I would just like to end the section on Titan by talking about the next mission, Dragonfly, which is being developed right now. It will actually land on the surface and use a hovercraft to pick up material from different places on the surface and analyze them chemically. You can see characterization. There are 4 different experiments that are used in this particular regard to characterize the carbon compounds. And so this will be an important closure to understanding the carbon processes that start in the upper atmosphere and end on the surface with a layer of organic material. We look forward to those results. Finally, I'm going to end with this slide. This is a slide that, in this case, since we accurately measured the various compounds in the upper atmosphere, we can say a little bit more about the distribution of the oxidation states of the various compounds. But starting off with the overall, if you just keep the methane in there, it's a very reduced atmosphere because it's dominated by the methane, which is a highly reduced form of carbon. If you remove that, you get a less reduced, but still reduced set of constituents, carbon constituents, that are generally more reduced than the parts that the carbonaceous chondrites or cometary material that we think forms them. And you can see that it's a kind of bimodal distribution, so it's quite different than what we see in the rings, and it's largely due to the processes of photochemistry that are happening in the upper atmosphere. Now let's move on to Enceladus. You can see several slides that indicate there's rays of material coming out of Enceladus. This is in the southern polar cap. This is scattered light of ice grains that are coming out of vents in the southern polar caps from this region that I've marked over on the right-hand side with a box that says tiger stripes. So these are areas of which are heated, as you will see, and material, both gas and ice grains, come out from the ocean and allow us the opportunity to sample this material as we fly by. Enceladus is a very small body in comparison to Titan. It's 10 times less the diameter of Titan. It has a lower overall density, so it's more water rich, but it still has water and rock, and that water and rock, as you will see, is quite interestingly distributed, with a surface of ice covering the surface, water, a water ocean below, and the rocky material and the core. I'll come back to this point. Note that the surface is at 75 degrees Kelvin, with the exception of these tiger stripes. In the next slide, I indicate some of the further attributes. So you can see on the far right, you can see that the plumes are coming out of these tiger stripe regions. The center slide shows a view, remote sensing from the thermal infrared, that indicate these tiger stripes are much hotter than the surrounding region because of the outflowing material, the outflowing water vapor that's coming out of the tiger stripes. And there's a lot of material coming out relative to the size of the body, about 200 kilograms per second versus 1,000 kilograms per second for Io in this Jupiter system from a much larger body. So a lot of material coming out that gave us the opportunity to analyze the composition. This shows some of the modeling that took place. I mean, if you're going to have liquid water in a very cold region of the outer solar system, then you need a source of heat. And it's the tidal interactions with Saturn and some of the other moons that provide that heating. That tidal interaction has been modeled, and it indicates, or at least the work by Shoemaker et al. Indicates that there is dissipation of energy not only in the rocky core, but in the ice and the water as well. But it's the rocky core that probably leads to heating processes that ultimately result in the outflow of material from the southern polar cap. Moving on to the next slide, we can put together a picture of the overall interior structure by looking at radio measurements that indicate the gravity, topography measurements, and rotation measurements from the imaging subsystem. And if we put all of this together, we see that there's a core density that's rocky, a core radius that's about 200 kilometers. Above that is a water and ice mantle layer that's 50 kilometers thick or so. The ice shell thickness and average is 20 to 25 kilometers, but the thickness in the southern polar region where the material is outflowing can get down to 5 kilometers thick or less. So we're looking at material that didn't travel very far to get out of the internal ocean. The thickness of the overall global ocean is of the order of 25 to 30 kilometers, and it is global. This shows a cutaway of some of our expectations of the geochemistry from what we measured. And some of the attributes that were measured, the cosmic dust analyzer was able to look at grains and determine that salts and bicarbonates are measured in the ice grains. I'll come back to some of this, but that's indication of salty material from an ocean. Organic compounds were found in the vapors and in the grains. We'll discuss this a bit further. Silicon dioxide was seen in the grains as well, and are an indicator that there may be hydrothermal systems in the interior. This was also demonstrated by the amount of H2 gas that was seen in the plumes. By our estimations, could only be made from serpentinization or geochemical processes in a hydrothermal system. So it's a very interesting ocean, perhaps with likely hydrothermal processes happening in the deep ocean. So let's start off and talk about each one of these different groups of compounds. First of all, let's talk about the gases that are just exhaled from the water as it moves up in the vents. These are very volatile species, and they do not condense out as they move up. They just travel up and exit, and we see them in the plumes. This gives an idea of the major composition of those gases. Water is the predominant by a long ways. CO2, CH4, so carbon dioxide, methane, ammonia, and H2 are important major constituents. Over on the left-hand side, you can see some other hydrocarbons and nitriles, as well as formaldehyde, that are other compounds that have been measured in the plume at lower concentrations. This slide talks a little bit about that more complex carbon compounds that are seen. Here's a list of possible compounds that are seen that have 3 and sometimes 4 carbons involved, and also have nitrogen and oxygen as part of the molecule. It's a very complex spectrum, and with the low resolution mass spectrometer, it's been difficult to deconvolve this material. Over on the right-hand side in the lower panel, though, you can get an idea of some of the major compounds that we think are actually present. And so those are likely existing. We're still doing work, and there's a poster in this AGU presented by Brian McGee that will just talk about the details of this evolving work that's going on at this time. This slide gives you some idea of how we developed a process. Chris Klein in particular worked on a process to try to relate what we're seeing in the plumes to what is seen in the ocean. And he used the total dissolved carbonate amount, the ocean, the pH, to determine the CO2 molality. And CO2 doesn't react with much of the material or condense out as it comes up. So that's used to scale all these other volatile, highly volatile materials and determine what their abundance would be in the ocean relative to each other. And so you see how we've scaled that for both CH4 and H2. And also note that since we don't know exactly what the pH of the ocean is, that it can range from 9 to 11, that the amount of these compounds that is dissolved in the ocean changes considerably with pH. This will become important later when we talk about energy for metabolism in the system. In addition to the vapors, there are ice grains that are formed from the water that is coming up. So there's like a spray of material that contains salts, and then as soon as that material is in this environment that's a near vacuum environment, there's a flash freeze of water on the salt grains, and so we form grains in the micron size range of ice grains that are blown out by the gases and later detected and measured for their salt content. You can see the cosmic dust analyzer spectrum that was used to perform this analysis, which was by Postberg back in 2009. You can see it contains sodium chloride, bicarbonate compounds, and potassium chloride compounds. All of these are familiar from the Earth's ocean. The salinity, though, is about a quarter that of the Earth's ocean. In addition to when these ice grains are flowing out, in the last portion where the vent is actually cooling, some of the less volatile gases that have moved up the column can also adsorb onto the surface of these grains and be seen. So let us talk a little bit more about that. This shows a slide that indicates that if you took the compounds that we potentially measured, which are indicated on the right-hand side, so the beautifully colored disc represents different compounds where there's an even distribution of that material on the surface. And if you allow it to equilibrate in that last portion of the vent column, you can see that those compounds become quite fractionated and are quite limited to things like acetic acid and to alcohol. So there's a fractionation process of this adsorbed material or these absorbed vapors but it does allow us to look at some of these other carbon-bearing compounds that have oxygen content, which is important. These measurements were made on the ice grains by the cosmic dust analyzer again. Here are shown the nitrogen-bearing compounds analysis in the upper panel, and in the lower panel on the right are the oxygen-bearing. And things like dimethylamine or ethylamine and acetic acid were seen. So there's some indication of materials that our observations of other gases and models would have predicted do exist absorbed onto the ice grains themselves. This is another way that material gets out of the vent, and it's an important way of consideration for the overall carbon inventory of the internal ocean. Finally, there's a very interesting set of compounds of high molecular weight. This work is recent work that has been published in Nature by Frank Postberg, but it has been observed by both INMS and by the cosmic dust analyzer in the course of the mission. In this case, large organic molecules come up and the ice flash freezes around them again so that the core is not salts in this case, but organic compounds themselves. This is an indication of a high speed. This is now INMS data. This is the first indication that we had that these particles might exist. You can see in the dark black low velocity flybys mass spectrum generated by that. And in the gray color, high velocity flybys. So there's a difference. There's more organic material present in the high velocity flybys. So this gave us an interaction or an indication that fragmentation of these ice grains was taking place in the instrument and that there were high molecular weight compounds potentially there. The smoking gun was actually found by the cosmic dust analyzer experiment by making measurements in the E ring, which is associated, is actually the ring attribute that is formed from all this outgassing from Enceladus. You can see a spectrum over on the left-hand side that indicates the complexity of the compounds can go up to 2,000 or 3,000 AMU. So they're very large organic molecules that are present in this material. You can see that in the lower panel on the right-hand side that there's a fairly periodic representation of some of these compounds in the intermediate mass range. And that same thing in some of these fragmentations also are indicated in the upper panel from the INMS measurement. So we can, from looking at all these fragments and the overall spectrum, we can kind of piece together that these are highly unsaturated compounds, but very complex organics that contain both nitrogen and oxygen. This would be one of the main things that one would want to go back to the system and understand the origin of this material. Finally, let's talk about the hydrothermal systems at Enceladus. The hydrothermal systems, as I've talked about, are generated by the tidal dissipation of energy in the rocks. The first evidence of this was the silicon dioxide nanoparticles that I mentioned that can only be formed under conditions that you might expect in a hydrothermal system. And as I mentioned before, H2, the amount of H2 in the plume was a further indication of the hydrothermal systems. And finally, the modeling that took place from Chablais also indicated temperatures that might be responsible for these hydrothermal systems. The schematic is just a pretty picture that shows how one might see at the rock-water interface of the southern polar cap the formation of hydrothermal vents. As I have already indicated, we were able to take our measurements of things like H2O, CO2, CH4, ammonia, and H2 and relate them to the amount of material that's present in the ocean. And from that, we could take look at chemical reactions, the thermodynamics of chemical reactions. One of them is represented here, 4H2 plus CO2 going to CH4 plus 2H2O, which represents a metabolic system of microbes in the Earth's ocean that have a metabolism called methanogenesis. And we were able to demonstrate that the chemical energy to support these kind of microbes is present in the internal ocean. The figure on the lower panel on the right-hand side indicate in the pH range we measured, the H2 to H2O mixing ratio would indicate that there is chemical energy present sufficient to support these microbes. And there have been some experiments done on Earth with simulating conditions in Enceladus that demonstrate that some of these types of microbes from the Earth's ocean could live under these conditions. This is not a claim that we've discovered life. This is simply a claim that habitability, metabolism could take place. There are other sources of ways that we can produce reductants and combine this with oxidants from the surface. Oxidants from the surface can be created from radiolytic processes both internal to the ocean, but also from impact processes in the ice, and the migration of the ice, the O2 and the H2O2 formed at the surface of the ice into the internal ocean. In the next slide, I show work by Christine Ray that is to soon be published in Icarus, exploring several different types of metabolisms that are present in the Earth that might be present in a system, and evaluating how much power one might extract from the expected chemical disequilibrium that these systems might create. So we see methane oxidation, hydrogen oxidation, we see anaerobic oxidation of methane, many things that we would be familiar in the Earth's ocean would also be chemically possible in this ocean. And finally, to summarize, the oxidation state, which is the point of comparison we've been using all along, you can see that if you include the CH4 and the CO2 that are measured, this would have a kind of typical oxidation state for a comet. But if you remove those compounds, it's a much more reduced environment from the chemistry that has taken place within the ocean, presumably. And in that particular case, you can see that the distribution is again bimodal and is a bit more like what we see in the case of Titan, where photochemistry in the case of Titan has modified the chemistry of the carbon compounds. In conclusion, let me just summarize with this slide. The carbon compounds that are infalling from the rings have an oxidation state close to that of comets and carbonaceous chondrites, which is what we had suspected earlier. The carbon compounds that are observed in Titan's photochemically active upper atmosphere are more reduced than those same reservoirs. If you take out the primordial volatiles that probably came in through cometary impact bodies to form Enceladus, you also find a situation where the secondary carbon compounds are in a more reduced state than the original materials, probably due to chemical reactions that have taken place in the oceans. Two caveats to these overall conclusions. One is that we must understand the effects of fragmentation. Fragmentation affects carbon compounds above 3 kilometers per second. And in all cases, the interactions with these bodies was done at velocities in excess of that. We've done a lot of work to try to understand this, and there's been a lot of modeling, but there's a lot of work still to be done to fully appreciate that process. Furthermore, we need to improve our ability to resolve these carbon compounds, to measure unequivocally the difference between nitrogen-bearing compounds and oxygen-bearing compounds. If we're going to comment on the future habitability of these places, understanding the details of the chemistry are important, so higher mass resolution is a necessity. And we must explore the surface materials, which is not part of what we've investigated with the Cassini-Huygens mission. Dragonfly represents a first attempt of doing that at Titan. Thank you very much for your attention. It was a wonderful experience to get to explore the carbon compound of the Saturn system, and sets a precedent for future missions to come.
Thank you so much, Hunter. This was a fantastic lecture. I don't see any questions yet. Often in these types of online meetings, people listen to the lecture in their own time. But I will make a comment about Titan. You mentioned that we're not sure that the organic material can get into the ocean. And that's one of the things that the NAI on Titan that I'm leading has been exploring. And in fact, recent work by Clara Kalasova and Christophe Sautin modeling the interior of Titan suggest, in fact, think it's quite likely that the ice layer between the core and the ocean, in fact, can have fractures and ways for the material to the core to get into the ocean. If you want a reference for that, you can just email me. And another interesting one about material from the surface getting into the ocean is, this hasn't been published yet, but we have been investigating impacts, and in fact, large impacts like Minerva, given reasonable conditions, could have gotten material into the ocean as well. And now we have a question from Fran Baganau. Great talk, Hunter. How do you think all this organic chemistry applies to the Jupiter system?
I was trying to turn off the other. My phone is speaking as well, so there may be some feedback. Let me see if I can get rid of it. Excuse me. Okay. Yes, friend, very good question. There certainly are the same types of physical processes probably taking place in an interior ocean at Europa. The formation is probably quite different, so the details of the chemistry are different. We hope to measure them. The difficulty could be the separation between the ocean layer and the surface and the accessibility of those compounds. As you know, with Cassini, we were quite lucky to be able to access that material rather directly. With regard to Titan, and in any kind of analogy there, we don't see any thick atmospheres in any of the moons of the Jupiter system. So that probably leads to a situation where the types of complex chemistry that we see at Titan are not likely on the moons of the Jupiter system, but we would have said that plumes at Saturn were not likely too. So we should all keep in mind that there's always new things that we don't expect to see. One thing I will note, Rosalie, is that on my screen, a couple of audience questions popped up that Heather sent me. Should
Okay. Yeah, go ahead. Go ahead. Because
let me
I don't
read the question. Yeah, it's under chat. That
Oh, yes.
I can read it. I can read it if you like.
Okay.
So can you comment on the relative value of doing additional fly-throughs of the plumes versus sending a lander to the Tiger Stripes to do in situ measurements of the chemistry in the South Polar region? Well, that's a very interesting question. It's got a kind of three-part answer to it. The first is anytime you're making claims like we did within the about Enceladus within the Saturn system, verification is always a good idea. And secondly, I hope I demonstrated in the talk that fractionation processes do occur between what absorbs onto grains in terms of semi-volatiles, the volatiles that come out that are just that are hard to that don't end up on the surface for the most part. They end up in free space. They escape the system. So it's important that we measure all of those things. I would say that the fly-throughs are quite complementary in many respects to putting together the complete chemical picture. And finally, I would suggest that the level of sophistication of the instrumentation that we propose for Europa with regard to mass resolution and sensitivity was largely based on our experience at Cassini. So many of the ambiguities that we have in understanding the chemistry of the internal ocean could be resolved with better instrumentation flying through those same plumes. That's true for both the dust and for the gas. And I see one more. Can you comment on the relative value of doing additional fly-throughs of the? No, that's the same one, isn't it?
Yeah. Yes,
Yes.
I'm not,
Do you see
yes,
any
the
other
same.
questions?
I don't see any other questions now in the chat.
Yes. So, okay. So if anybody else has any questions, I think we got a minute or two more, but
I
this format is a little bit different. So I
Yeah.
think we all have to get used to it.
Yeah, we have just about 1 minute, so we really look forward to Dragonfly and to give us even more measurements from the surface. So we'll have the inner mass and the sears at different altitudes, and we had Huygens, and then with Dragonfly, it should really give us a good picture, and maybe a mission to Enceladus.
That would be nice. Very interesting body.
Yes. All right. And just wanted to thank you again. This was a really fantastic talk. And I know it's difficult to do a talk when you're recording it. And you did a fantastic job. Um,
Thank you. And it is different to do a talk and record it.
right. Uh, and we are seeing uh, many thank yous here. Lucy McFadden and John Connerly has said that people are experiencing difficulties accessing your talk. And all I can say is, try later because the talks will be available for some time. I to
Well,
all
I
the
would certainly add, if they look at it, if they're able to look at it later and they have further questions, they should feel free to email me at hwaite@swri.edu. Be happy to answer any questions anybody has.
Dave Williams also says thank you, great talk, and also Jun He is thanking you. So it's good. We did have a live audience, despite the all the different time zones.
Thank you, Rosalie.
And Stephen Bauer says thanks, Hunter, for a great talk. So I will. I'll even listen to parts of it again. Then I learned a lot. So thank you so much.
Thank you.